today let's start talking about series. So these, the two words, sequence and series, they mean different things, although sometimes people confuse the two. But a sequence is just a list of numbers, one after another. A series is what you get when you add up all the numbers in the sequence. Is the sum of all terms of a sequence. So if we have a sequence, for a sequence, which we usually write like a sub n, the series associated to that sequence is the sum an, right? And when we write the sum, typically we'll write, a little something like n equals 1 to infinity, that kind of thing. The sum of an's. My Zoom screens are really quite blurry here, I can tell. Sorry about that. I'm going to try and write big. Please shout out the folks at home if you can't see something. Let me know. I'm happy to clarify. All right, this is what a series is. Like I said, we will, to avoid confusion, we will typically write this little n equals 1 and infinity. But sometimes we will, if there is no confusion, we can just write the sum of an, right? The sum, it just means you add them all up. And I mean, since it's a sequence, like by default, the n starts at 1, and of course it goes to infinity. That's where it goes for any sequence. All right, so sometimes we're just going to write the sum without the little guys on it, okay? This is called a...
Let me ask you a quick question.
Yeah, sure.
This looks very familiar to a statistics formula, for like a variance formula, maybe?
Maybe. I mean,
do you know if they're like interrelated or something like that?
Well, in statistics, you use that summation very often. Although in statistics, it's usually not an infinite. Sometimes what we're talking about here is sometimes called an infinite series because you add together sort of forever up to infinity. In statistics, usually you don't do infinite sums, but you can write a lot of statistics formulas using the summation sign. Like for instance, the mean of, if you have, say, x1 up to xk, the mean is equal to 1 over k times the sum of xi, I equals 1 to k, something like that. I mean, and yeah, you said the variance is similar to that, and many other things. Although it's usually not the sum up to infinity. Like, you don't typically talk about the mean of infinitely many things. At least not in real world statistics. You always have just a finite amount of stuff. Okay.
Perfect, thank you. That makes sense.
Yeah. So we actually have talked about one example of an infinite series before, although I didn't really say it in these words, but we did talk about, when we talked about improper integrals, we discussed this 1 plus a half plus 1/4 plus 1/8. I don't know if you remember this, but this was based on, we were trying to demonstrate that sometimes the area under the curve, even if it stretches out forever, sometimes the area under the curve can be finite. And I gave you some kind of very specific argument about this particular sum here. I don't know if you remember this. I had these like two boxes. This is the one. When you add in a half, it's here. When you add in a fourth, it's like that, etc. This actually adds up to 2, right? We talked about that as an example. This kind of thing is what we want to discuss in this section. How could you add this up and get 2 as the answer without like drawing that little picture? Or what if those numbers were different? These, you can tell these are powers of 2 in the denominators here, but what if instead I used powers of 3, say? Not 81. 27 is the next power of 3, right? Equals what, right? You can't, there's no like convenient picture to draw with the boxes in this case, because you get 1/3, like instead of filling up a half of the remaining area, you fill up only a third, and it gets complicated, the numbers. But by the end of today, maybe, provided we get far enough, you will actually be able to add these up. So we're going to talk about, if I give you a series, how can you actually figure out what the answer is? What does it add up to? All right? But before we get to that, we should discuss what does it even mean to add something up sort of to infinity, all right? So first, we actually need a definition. Definition of this sum n equals 1 to infinity an. What does it even mean to add up infinitely many things, right? It's not obvious what that means. It will not surprise you that we define this in terms of a limit, right? I mean, basically everything in calculus or whatever, which involves doing something sort of forever or to infinity, the only way you can make sense of that is as a limit. Now, it's not entirely obvious what exactly is this a limit of. The way we set this up, though, is you just imagine, instead of adding together infinitely many things, you just imagine you added like a whole lot of them together, and then you kept on adding more and more, sort of one at a time. Add one more, one more, one more, one more. And then you take the limit of that, all right? That's sort of how we formulate the limit here. Here's the official way that we write this. So given any sequence an, we define another sequence, which is related to an, another sequence, which I'll use S's for. S1 is just A1. S2, S2 is A1 plus A2. S3 is A1 plus A2 plus A3. So this sequence S, the letter S is for sum. S is the sequence of sums starting from the beginning and just going up a certain amount and then stopping, all right? So each of these S's is a sum of part of the series, right? The whole series includes everything, but these guys, they just go up to a certain point and then they stop. So Sn in general is A1 plus A2, etc., up to an, all right? And this S here, this sequence, Sn, is called, it has a name, it's called the sequence of partial sums. All right? Sums because they are sums, you know, adding stuff together. Partial, the word partial is indicating that they are not the entire series. The whole series includes infinitely many things. These are just part of it. Each one represents part of the whole series. Another way you could write these is Sn, as written another way, is something like the sum from I equal 1 to n of ai, right? That's the same thing that I wrote up there, just using the summation sign. And I'll just point out, each Sn is not a series. It's just a sum of finitely many things, right? When I say the word series, that means a sum of infinitely many things. This is a sum of finitely many things. And so it doesn't require another definition. Like, if you ask me what does that mean, it means something very specific already. You just add n things together, all right? Anyway, the definition then. So the definition, I wrote derf. I meant def. D-E-F. The definition is the sum n equal 1 to infinity of an is defined to be the limit as n goes to infinity, sum I equal 1 to n of ai. Of si. What? This is totally bogus. There should be no sum here. Actually, what I just wrote was correct. It's not what I meant to write, though. It's just this. This is what I wanted to write. The lim n goes to infinity of Sn. All right. These sums individually represent adding together n things. and you take the limit as n goes to infinity. And that's how you make sense of adding together infinitely many things, all right? It's a limit of, what if I added just the first n? Then you take that limit of that as n goes to infinity. All right? Another way of writing this is you could just say it's equal to the limit as n goes to infinity of, a1 plus a2 plus etc. all the way up to an, right? I just wrote, that's what Sn is. It's that little sum in there. All right, this is the definition of the series, and because it is a limit of something, let me just point out, it may converge or diverge, right? Everybody knows that limits sometimes converge and sometimes diverge, and therefore, the same is true of a series. Sometimes the series converges, and sometimes the series diverges, according to that limit there, if the limit exists or not. All right? So here's a simple, I want to do two simple examples. You will see pretty quickly that computing the answer of a series is, in general, quite difficult. And we're going to learn sort of a bag of tricks. But there is no one method which will always work to compute the answer of a series. But sometimes it's easy enough that you can just say what the answer is. Let's say that an is the sequence 1, 1, 1, etc., right? Every term equals 1. And I would like to say, let's show that I just want to show the series of n equal 1 to infinity, equals infinity in this case. What I mean by that is it diverges, and in fact the value is going diverging to infinity. All right. First of all, do you believe this? I mean, this should seem completely unsurprising as an answer. If an is 1, 1, 1, what I'm doing is adding together 1 every time. So this, if you were to write out the sum here, this sum here is 1 plus 1 plus 1 plus 1, etc., right? And I hope everybody agrees. If you just add 1 over and over again forever, the answer will be infinite, right? When I say the answer equals infinity, what I mean by that is what you get if you continue adding terms in the series is something which goes to infinity, right? So, totally unsurprising. How would we actually demonstrate this? Well, remember, so to show it, remember the definition is sum n equal 1 to infinity of an. The definition is this is equal to the lim as n goes to infinity of Sn, right? The limit of the partial sums. And can we say what Sn is? Actually, it's very easy to find a formula for Sn. Maybe I'll do this off on the side. Remember, S1 is A1. S2 is A1 plus A2. S3 is A1 plus A2 plus A3, etc. But in my example here, An, every term of the sequence is always 1. So A1 is 1. A1 plus A2 is 1 plus 1, which is 2. A1 plus A2 plus A3 is 1 plus 1 plus 1, which is 3, and so on. Can anybody say, in general, Sn, the nth term of the sequence, can you tell me a formula for this? I mean, it's going to be 1 plus 1, etc. What's it going to equal? Can you see the pattern?
It's infinity, right?
If I add together just Sn, so this, remember, Sn does not add, this is not adding all of them, it's just adding the first few, right? In fact, the first, here's the S1 is the first one, then we have the first two, then the first three.
Would it converge to 6?
6? How do you get 6?
Or 1 plus 2 plus 3?
I'm not trying to add those things. S, so S1 means 1. S2 means 1 plus 1. S3 is 1 plus 1 plus 1. How about Sn then? I think somebody said N. Did somebody say N? Somebody said something which rhymes with N. I'm going to... It would be N. Yeah, because this means we add up 1 plus 1 plus 1 plus 1 a bunch of times. How many times? N times, because I'm talking about Sn. And so it adds up to N here. That's what I was going for. All right. So where I was back here, we are finding the limit as n goes to infinity of Sn. And we just said Sn equals n. So this is actually lim n goes to infinity of n. But that, of course, equals infinity, right? When you take the lim as n goes to infinity of n. The limit here does not converge, and in fact, it goes to infinity. So this is how you demonstrate. What you have to do to evaluate the answer of a sequence, of a series, is you find a formula for Sn, and then take its limit, right? This is the method. Find a formula for Sn, then take the limit. And in this example, the formula was Sn equals n, because Sn was just 1 plus 1 plus 1 n times. That adds up to n. All right? Any questions about that one? All right, let's do one that's a little less obvious. Like in that example, I think it was pretty obvious that you were going to add up to infinity. If you just add 1 over and over again forever. How about maybe a little more interesting? An equals minus 1 to the power n. Which, of course, you know, when you write the terms out, it's minus 1, then 1, then minus 1, then 1, minus 1, 1, etc. All right? And I would like to know what is the sum of an, right? In other words, this is the sum of minus 1 to the power n. If I were to write out the terms of this, it's negative 1 plus 1, minus 1, plus 1, minus 1, plus 1, etc. All right? Now, this one is a little trickier to decide, to have some idea going into it. First of all, I would say this is not going to be infinite. It doesn't seem to be infinite because if I'm adding negative 1 and positive 1, there's some like cancellation, right? In fact, maybe this is 0 because you could pair these things up in a way that they all cancel, right? If you add pairs of them. It turns out, actually, the answer is not 0. The answer is that this series diverges. Some weird things can happen with series that are a little counterintuitive sometimes. But anyway, don't take my word for it. How are we going to do this? We do the same thing that we did in the previous problem, which is, first of all, try to find a formula for Sn, and then take the limit of that formula. So let's find Sn, all right? Remember, S1 is just A1, which is negative 1 in this example. S2 would be A1 plus A2. In this example, that would be minus 1 plus positive 1, which is 0. S3 is the sum of the first three. Can I just write minus 1 plus 1 minus 1? Right? You take the first three things. This adds up to negative 1. S4 is the first four things, which is 0, etc. Can we see a pattern here in the answers? I would like to say something about Sn. This is not really something you can write in a nice formula, but anyone want to try and describe the pattern in words? I'm looking at these answers here.
Well, it's a pattern of zeros and ones, or negative ones.
Yeah, zeros and negative ones.
Yeah, I'm not 100% sure how you would express that in a formula.
Y- Yeah, this one actually is not easy to express in a formula, but I would say it's just alternating from, minus ones and zeros, right? So would I say maybe one thing I can say is the terms are, negative 1, 0, negative 1, 0, negative 1, 0, right? These are the terms of Sn. Now, as a formula, I don't. It's not convenient to write a formula for that. I mean, it's possible, but I wouldn't. I wouldn't say it's very useful, and I wouldn't try too hard to write a formula for that.
Did you just say that S of negative or S of odd numbers is -1 and S of even numbers is 0?
Yeah, you could say that. So you could write the formula like this, something like Sn equals -1 if n is odd, or you could say 0 if n is even. Right? That's one way you could write this. If you really wanted to be super fancy about it, you could say Sn equals, check this out. See how you like this. Negative 1/2 plus 1/2 times minus 1 to the n. I think that will give you this sequence. But I don't really care about that. That's a very fancy formula for getting a sequence like this. None of this really matters. All we care about is the limit of Sn, right? What is the limit as n goes to infinity of Sn, right? Using the formulas are not so helpful. You can just look at this sequence here and ask yourself, does this sequence actually approach any particular value? And the answer is no. It just bounces back between two different values, right? It's -1 and then it's 0, and then it's -1 and then it's 0. So this limit does not exist. That sequence, however you want to think about it, it's not even necessary to write a formula. It does not, that sequence does not have a limit because it doesn't approach a particular value as you go down the list. It just bounces back between two values. And so that means the sum of the an, this of course equals the lim of the Sn, this diverges, right? Does not converge to any particular number. All right. Even though you might feel like like I said before, I don't know if you were hip to my little informal argument here. I said you could pair them up like this and they'll all cancel out. All right. What I was expressing is the fact that on the even terms, the sums, the partial sums, actually do equal 0. So if you take only an even number, you can pair them up in that way, and they all cancel out. That's true. But if instead you took only an odd number, they would not all cancel out. You'd have it left over -1. And so who's to say? Are you going to get like 0? It alternates between being 0 and being -1. And so it does not converge. All right? The series diverges. That's a little disappointing, perhaps. I don't know. Let's talk about one. So those two examples, both of them diverged, right? The first one diverged to infinity. This one just kind of diverges because it doesn't have a particular answer. It oscillates between two different answers. Here's an example. An example of one that we actually can do. Like it's actually going to converge. Let's try. This series is a major example that we're going to say quite a bit about. It is the sum n equals 1 to infinity of r to the power n minus 1 for some value, some number r. All right. This actually falls into the category of the examples that I mentioned at the very beginning when we started talking about this. If you were to write out the terms here, this looks like r to the 0, r to the 1, sorry, I shouldn't put commas, I should put pluses because this is a series, right? R squared plus r cubed, etc. right? R to the 0, of course, is 1, but those other numbers are just whatever they are. So this would be 1 plus r squared plus r cubed. All right? And for various r, actually, these come up and fairly often in the real world and also, just in sort of the world of mathematics. For example, so let me just say, we'll compute the answer for any r. So there's actually a formula for what this adds up to, a formula based on r. And it's a very simple formula, so it's not a big deal. But for example, one example would be r equals a half. What do you get if you use r equals a half? Then it looks like 1 plus a half plus 1/2 squared plus 1/2 cubed. Oops. Of course, you could also write that as 1 plus a half plus a fourth plus an eighth. And we know, just because I said so, this adds up to 2, right? That was the example I mentioned at the very beginning. And once you know the formula for the sum of a series like that, it's very easy to show when you plug into the formula, you get 2 for the answer, all right? And you can use that same formula, you could plug in 1/3, which is the other thing that I asked about at the beginning. What if instead of 2's there, powers of 2, you have powers of 3? What would that add up to? Well, if you know the formula, it's easy to answer all of these questions, all right? Let's see if we can come up with this formula. So the formula, coming up with the formula involves a slightly weird trick, which is not obvious. I would say, I mean, I probably wouldn't come up with this trick. Maybe if I thought about it for days on end, I would come up with a trick like this. But it's a cute trick. So in this case, let's say it involves looking at the sequence Sn. S1, of course, is just 1. Remember, the series looks like 1 plus r squared plus r cubed, right? This is what we're talking about. So S1 would be just the first thing. S2 is the first 2 things, which would be 1 plus r. S3 would be the first 3 things, 1 plus r squared, etc. To write Sn, it would be 1 plus r squared plus r to the n minus 1. You can see that these numbers are sort of off by 1. S3 goes up to r squared. So Sn will go up to the r to the power n minus 1. All right. When you write this formula for Sn, though, it is still not at all obvious how to take the limit as n goes to infinity of this. And really it's because of these dots here. This dot, dot, dot makes it difficult to say what is the limit as n goes to infinity of this. We can sort of simplify this formula for Sn, though, so we can find a better version of this formula, a better formula for Sn by doing some very, I would say, weird but simple tricks. All right, and here's the trick. The trick involves, first of all, instead of considering Sn, I would like to consider r times Sn. What do you get if you do r times Sn? Well, that's easy enough. Just using this formula, Sn here, I can multiply through everything by r. The effect is to increase the exponents by 1 every time. So r times Sn, instead of starting with 1, it starts with r, then r squared, then r cubed. And it finishes with r to the power n, right? I distributed, multiplied through everything by r, which has the effect of increasing every exponent by 1. All right, this is r times Sn. And now, the second sort of cute step is I'm going to subtract Sn minus r times Sn. All right? And what I'm subtracting is, here and here. And the point of this is, you'll see, when you subtract, actually those 2 things are almost all the same. Most of the terms of Sn are the same as terms of RSN, right? They're almost all the same, and so they're all going to cancel when you subtract them, except there will be a few things left over. Can anybody say what's left over when I subtract there? Most of it cancels, but not quite everything. Maybe one of you folks in the room. Can you tell me, Julian? Maybe not. Or Gabriella. Avoiding eye contact. We're subtracting the top one here, so I could write it, 1 plus r squared, rn minus 1, and then subtracting from that, I'm subtracting, I'll write it down here, r plus r squared plus r cubed. Most of those will cancel. What's left over? Yeah, the 1 is left over at the beginning. There's nothing which cancels the 1 when you subtract here. And there's one other thing which is left over which doesn't cancel. Yeah, r to the n, because this first one only goes out to power n minus 1. So when I subtract, it does not, there's nothing to cancel with the r to the n. Great, thank you for that. 1 minus r to the n is what you get. Everything else in the middle cancels, but the two, the first thing, the 1 has nothing to cancel with, and the r to the n has nothing to cancel with. Okay, great. This, I'm just going to write the left-hand side again. This is Sn minus r times Sn. And now we can solve this for Sn. And we get a different formula for Sn than what we started with, which is more useful. How would I solve here? I would factor on the left Sn times 1 minus r equals 1 minus r to the n. And then I can solve. Sn is 1 minus r to the power n divided by 1 minus r. All right. That's an n up there. Make it a little clearer. All right, this is our improved formula for Sn. And let me just say, when r is not equal to 1, because I just divided by 1 minus r, obviously this formula cannot be true when r equals 1, right? Because then the denominator would be 0. So that's a special case when r equals 1, which this formula does not work. But in all other values, for all other values of r, this is going to be the formula for Sn. And so that means my original series, remember the series I was talking about was n equals 1 to infinity, r to the power n minus 1. It is equal to lim n goes to infinity of Sn, as always. This is the definition of the series. But this, I can now put in my nice formula for Sn. 1 minus r to the n over 1 minus r. And what is that limit? Well, by our old limit rules, you can really just kind of, all we care about is the r to the n part, because everything else is just a constant. Right? This part up here is the only thing that matters, the limit of r to the n as n goes to infinity. And that part, I don't know if you remember, but this is something that we talked about at length in the previous section about the, I call this a geometric sequence. And we talked about the limit of such a thing. This limit here, I will refresh your memory. The limit as n goes to infinity of r to the power n equals 0 if r is in this interval. Ooh, sorry. Come on now. Remember this? It equals 1 if r equals 1, and then it diverges for all other values. Sorry, I wrote right under the sign there. This is what we talked about maybe last time, maybe 2 times ago. I don't remember exactly. It diverges for other values. Remember that? And so the same sort of things I can say here. Well, what I want to say is this limit right there is going to be 0 for the most of the time, right? The only time it's not 0 is this, when r equals 1. But we've already seen actually that's already a special case. We are not considering r equals 1 when we're using this formula. And then it diverges for other values. So this part, that limit right there is going to be 0. And we just get this, all right? Now this formula is not always true. It's only true in the case when that part of the limit is 0. But this is true when r is in this range right here, between -1 and 1. And I'm going to write that just because it's easier to write this way. Absolute value r less than 1. All right? That's the same as saying r is between -1 and +1. Just a simpler way of saying that is absolute value r is less than 1. All right, you should put this in a box somewhere. There's a name for this. This is called the geometric series for obvious reasons, because it amounts to the geometric sequence. And this is the answer you get from the geometric series when the absolute value of r is less than 1. And actually, the box, maybe the box should be a little bigger. Sorry, I know you already wrote the box, but when the absolute value of r is greater than 1, greater than or equal to 1, the series diverges. The sum r to the n minus 1 diverges. That's because when the absolute value of r is bigger than 1, then this limit up here diverges. I said it diverges for the other values, right? Now, what about if r equals 1? Well, if r equals 1, then what we're talking about inside the sum is just a sum of 1 over and over again. If r equals 1, this term is 1 every time. And so it looks like 1 plus 1 plus 1 plus 1, which we've already seen that diverges, all right? So it's a very simple kind of two-parter here, right? If the absolute value of r is less than 1, then you have this formula. You get 1 over 1 minus r. And I guess you should memorize that formula. I mean, it's simple enough. We're going to use it all the time. That formula works only when the absolute value of r is less than 1. And in the other case, when the absolute value of r is more than 1, the series diverges. All right. Let me just say a slight generalization. More generally, if I'm looking at, instead of just a power of a number, let me say again, if absolute value r is less than 1, this happens a lot actually, that we have a constant times powers of r, all right? Now, we're going to talk about this eventually, but when you have a series like that with a constant multiple, if it converges, then you can factor the constant out of the sum. This is not a surprise. You can do that with ordinary sums. You can also do it with infinite sums. So this, it turns out what you get is simply going to be a times the answer of the series up here. So I'm going to write this, but multiplied by a, because you can factor the a out here. What it looks like is this, a over 1 minus r, right? This is the formula for a geometric series that has a constant inside, all right? And this is what we're usually going to use. And of course, if the absolute value r is greater than 1, it diverges, all right? In general, this kind of sequence comes up all the time. So generally, any sequence like this format, an equals a times r to the n minus 1, where a is some specific constant, this is called a geometric sequence. I used those words last time. If you write out the terms, it begins with a. The next term is a times r. then a times r squared, then a times r cubed, etc. All right. This is called a geometric sequence. One thing you will notice about such a sequence is that if you divide any term divided by the previous term, you always get the same answer. In this case, if you divide any term by the previous, what do you get? Like, for instance, the second one divided by the first one, AR divided by A is R, right? Or if you divide, say, the third one divided by the second one, AR cubed divided by AR squared is also R. These things cancel out and you just get one R left over. This is a basic fact of a geometric sequence, is that when you divide any term by the previous term, the answer is always the same, and it is always R. So this R, for that reason, R is called the common ratio of the geometric sequence. Common meaning like it's the same every time. Every ratio, if you ever divide one divided by the previous one, you're always going to get the same number, and that number is called the common ratio of the geometric sequence. All right. So actually, if you have a geometric sequence, it's easy to figure out what the A and the R are. Sometimes these can be a little tricky to recognize. For instance, I'm going to write some terms here. 2, 6, 18, 54, etc. It turns out this is a geometric sequence. You know, it is possible to write this in the form A times R to the n minus 1. How could we find the A and the R? It's very easy if you know that R is the common ratio. And what is the A? Well, actually, the A, remember the sequence looks like this. The A is just whatever the first term is, right? It starts with A. So that's very easy if you know what you're doing. So here, A is 2. A is always equal to the first term. And what's the R? The R is the ratio of each term divided by the previous one. And you can choose whichever one you want. You might as well just choose the 6 divided by the 2, right? R is the ratio of each term divided by the previous one, which is 3. This is the common ratio, right? And so immediately I can say what my formula is. So this sequence, so this one was apparently an equals 2 times 3 to the n minus 1, which is, I mean, that's not exactly obvious if you just look at the numbers, but it's easy to figure that out. 2 times 3 to the n minus 1. And then our formula for that, our formula for the series, remember? If absolute value r is less than 1, then the series of a r to the n minus 1, it equals a over 1 minus r. So the sort of simple way to remember this answer here, the a is the first term, and then the r is the common ratio. So this is one, I mean, the book says this is a helpful way to help you remember the formula. I don't know if it's so hard. Maybe you can just memorize the formula as is. But anyway, this is how it works. It's the first term on top divided by the common ratio on the bottom. Of course, this only works when r, the ratio, is less than 1 in absolute value. And if r is bigger or equal to 1 in absolute value, then the series diverges. All right? All right, we got 10 minutes. Let's just do a couple of quick examples. I had some for you to try, although I don't know if we're going to, we probably have enough time. These are pretty easy once you know the tricks. So here's an example. How about find, oh man, find the sum. I'm not even going to write it like a series. I'm just going to write the terms out. All right. Assuming that this is a geometric series, can we evaluate the answer? Or perhaps it diverges, right? That's an option also. I would say we should first determine what is the A and the R. This is very easy. The A is the first term, so it's 2. And the R is that ratio, each one divided by the previous. So I'm just going to take the first 2 terms. The second is -1 divided by the previous one, which was 2. All right, so the R is -1/2, and the A is 2. So what's the thing add up to? First of all, it does converge because absolute value of R in this case is 1/2, which is less than 1, so it converges. And then the answer is A over 1 minus R, right? Which is 2 over 1 minus -1/2. Which, if you wanted to simplify, it's 2 over 3/2, which is 4/3, right? That's the answer. 4/3, in my opinion, this is a very strange answer to that. You know, what you're doing is adding and subtracting fractions with denominators which are powers of 2. It somehow all adds up to 4/3. Very weird, but weird things happen in a series. Any questions about that one? How about, can we do that one I said just at the very beginning? How about this one? Now, I know the answer to this is going to be 2, but it would be nice to see that you actually get 2 when you use the formula, right? What do we got? You got to figure out the A and the R. The A is just the first number, which is 1. The R is the ratio, each one divided by the previous one. I'll do 1/2 divided by 1. Of course, that's 1/2. So R is 1/2. Does it converge? Yes, it does, because the R is less than 1 in absolute value. And what does it converge to? So the series, I'll just say the series equals A over 1 minus R, which is 1 over 1 minus 1/2, which is 1 over 1/2, which is 2. Confirming what I told you so long ago by drawing the boxes. You really do get 2 according to that formula. All right? What if you use powers of 3 in there instead of powers of 2? 1 plus 1/3 plus 1/9 plus 1/27, etc. What's it going to add up to this time? Well, you just plug into the formula, right? Again, the A is 1 in this case. The R this time is going to be 1/3 divided by 1, which is 1/3. Plug it all in and work it all out. It does converge because R is less than 1, so I get A over 1 minus R. This is 1 over 1 minus 1/3. This is 1 over 2/3, which is 3/2. 1/2. So it's less than 2. That's not a surprise because I increased all those denominators. It adds up to 1/2. All right. This is the sum of a geometric series. Now, I had some fancier examples, and I wanted you guys to try some, but I think maybe we'll leave it for next time. I know we got 5 more minutes, but not enough time to get too fancy. All right, that'll do it. Check out the homeworks this weekend. We'll include the improper integrals. Sorry, I forgot about them last time. All right, have a good weekend.
Take care.
Thank you. Have a nice weekend.
Thank you.
Mm-hmm.